Hello, welcome to the series of lectures in physics that give a brief idea about the concepts in various topics coming under physics. And the present topic, what we have selected is for discussion is the derived units and supplementary units that comes as part of the chapter called Units, Dimensions and Measurements. In physics deals with the objects seen around us, and we need, for the measurements purpose, we need to have three physical quantities to be measured. That is length denoted by L, and mass, the content in the matter contained in the object, and the time of its presence at a particular time. So the length, mass and time are the three fundamental units, dimensions required for studying the mechanics in the physics area. And when you are dealing with other uh, branches in science and engineering aspects as well, then you need to have four more units like temperature, current ampere, and light candela, and mole, the matter, when you are talking about the matter contained in a particular gas or whatever it is. So, as far as mechanics is concerned, three fundamental length, mass, and time are adequate for studying the various phenomena. The dimensions, generally they are designated in square brackets, like the shown in the figure, m in the slide, m, l, and t. And the dimensions also must have include the powers. That is, uh, when we are talking about this particular quantity, it may have a length unit or not, or say mass unit or not, time unit or not, we don't know. So, if nothing is there, the MLT in the next point discussion. If you are talking about a dimension for length, then the dimensions are for the length are given as m0 because mass is not there. So m to the power of 0, that means there is no mass content in that. L content is 1 to the power of 1, and time is not there, so time to the power of 0. Similarly, if you see for frequency, that is cycles per second, that is per second is the unit used for that. So its dimension is mass is not there, so m to the power of 0, length is not there, l to the power of 0, and time is coming in the denominator part, so it is t to the power of minus 1. So this is how we have to designate the dimensions for a physical quantity. Such representations we call that as a dimensional formula, and also when a particular physical quantity is a combination of two or three other quantities, like velocity is equal to initial velocity plus product of acceleration into time. So this kind of equation, that v is equal to u plus at, which we write in mechanics first equation, linear motion equations, then that such kind of equations are called dimensional equations. Even this formation of such equations also should satisfy the requirements comes under dimensional analysis to in preparing the dimensional equation. And there are three systems, measurement systems, that means units. Units are centimeters, grams, in seconds, in CGS system, old one, CGS system. Length is measured in centimeter, mass is measured in grams, and time in seconds. And the British system, FPS, that is foot pounds second system. Length is measured in feet, m is measured, mass is measured in pounds, and time in seconds. And now currently universally used systems are MKS system, SRSI system, Standard International Systems, in which length is measured in meters, M is measured in kilograms, and T is measured in seconds. The SI system has got certain advantages as compared to CGS, FPS, and other MKS systems. And any physical quantity, because there are three different measurement systems, CGS, FPS, SI, MKS, like that. So from one unit to other unit, if you want to compare the physical quantity, suppose 1 meter is there, 1 meter cannot be changed. But 1 meter you want to say, you want to express it in a CGS system, then you must have some equation for that. So all physical quantities should contain a numerical number also. That means 1 meter or 10 meters or 1 kilometer. So this kind of that 1 is the numerical value. So numerical value n, q, physical quantity q should be given in terms of a numerical value and the unit whatever you are presenting, whether it is centimeter or gram or whatever it is. So q is equal to nu. When you want to express from one unit to other unit, that q is fixed, that cannot be changed. So n1 u1 is equal to n2 u2. Whereas u1 is one measurement system, u2 is another measurement system. Here I have shown example. If we want in the first n1 u1 unit is meters and n1 is 1 meter. 1 meter you want to convert into centimeters CGS system. So U2 is centimeters, N2 is 1, but you want to bring meters into picture. So 1 meter is 100 centimeters, so 1 centimeter is 1 by 100, so 0.01 meters is the unit. Here, thus, the N1 is equal to 1 and N2 is equal to 0.01, while U1 is meters and U2 is in centimeters. So like that, you can convert from one unit to other units. Then, in addition to this length, mass, time uh, system units, dimensions, you can derive other units also, either these combination of these three or combination of all these 7 units which are used in science and engineering studies. So like that, one examples are given here. They are called derived units. That means when you combine few units and a few dimensions and then bring it into one another physical quantity to describe another physical quantity, then they are called derived units. For example, area. Area is length into breadth or width. So that is length is also dimension is L, width is also dimension L. So it is L into L, that is L square. So its dimension is L square and unit is meter square. Similarly, volume, length into width into height. So it is meter cube is the unit in SI units, of course, and the dimension is L to the power of 3. So here M is 0, T is 0. Only length dimensions are there in area and volume. When it comes to density, mass per unit volume, the kgs per meter to the power of minus 3 per meter cube. So mass unit is 1, length unit is minus, dimension is minus 3, and time dimension is 0. So it's a dimensional m0, m1, L to the power of minus 3 and T to the power of 0. When you talk about velocity, which is a distance traveled in the given time, unit time, that is meters per second. So its dimension is length L to the power of 1, m is 0, T to the power of minus 1. Acceleration, it is the rate of change of velocity again. So meters per second square, that is the unit, and dimension is m is 0, m to the power of 0, L to the power of 1, T to the power of minus 2. M is not there, so LT minus 2 is the dimension. Force. Force is given by mass into acceleration. Its unit in SI unit is newtons, otherwise it is kg meters per second square. So kg is mass is there, so m to the power of 1 meters per second square. So LT minus 2 for the acceleration. So MLT minus 2 is the dimension for the force. Pressure. When force is applied on an area, the pressure is created on that area, that is force by area. Force again newtons, that is kg meters per second square, and by area is again by meter square. So its unit is newtons per meter square, and the dimension is m l minus 1 t minus 2. Momentum. Any moving body, a body mass having mass is moving with a velocity, then it is supposed to set to be having a momentum of mass into velocity. Mass momentum is given by mass into velocity. P is equal to mv. So mass is kg, velocity is meters per second. So kg meters per second is the momentum unit. So its dimension is mass is there m, length is there l, time is in the coming in the denominator, so t to the power minus 1, mlt minus 1. Work. When force is acting on a body, if it causes displacement in the body, then we say work is done. So work is given by force into distance, that is Newton meter. Force is the Newton is the meter for the force, distance is in meter. So the dimensions are m, l2, t minus 2. Power, that is rate of doing work, that is the ability to do stored energy. The power is the ability to do work. That is given by work by time. Its unit is watts. So dimensions are m, l square, t minus 3. Impulse. When force acts over a short time, then the body is supposed to be experiencing impulsive force. So that is given by I is given by force into time. Again Newton seconds, m, l, t minus 1 is the dimension. Torque. Shafts, rotating shafts are expected to have tangential forces acting on that for its rotation, and that force into diameter will give the torque. So force into distance, that is Newton meter is the unit, and ml square t minus 2 is the dimension for that. And potential energy and kinetic energy. A body at a particular height h, if its mass is m, the potential energy is given by mgh, so many joules, energy is given in joules, and its unit is ml square t minus 2. So kinetic energy also joules is the unit. So dimensional energy is m l square t minus 2 half mv square. So unit is dimensionally both should be same. And stress, when a body is acting upon a force, then the force by its cross section area, body's cross section area, that means force is acting perpendicular to the area. So this force by area is called the stress. So newtons per meter square is the unit for that, and dimension is m l minus 1 t minus 2. Strain. When force is acting on a wire or body, then it stretches under the force. So extension produced in the body over its original length is called strain, that is extension produced in the body. Because both extension and length are in the same unit length units, so there will be no units, and it's a dimensionless quantity strain. Then elasticity. Elasticity is the ratio of stress versus strain, because strain doesn't have any units or dimensions. So elasticity dimensions and units are same as stress, that is Newton per meter square, and ml minus 1 t minus 2 is the dimension. Coming to the current electricity topic, current density. When through a wire some current is passing through some area, current passing per unit area, that is current by area, is known as current density J. J is equal to current by area. Its unit is amperes per meter square. So A L minus 2 is the dimension for current density. Similar to magnetic field, when a current carrying conductor is known to produce magnetic field surrounding it with decreasing strength as the distance is increasing. So the magnetic field strength at any distance r from the length of the wire is given by current passing through the wire by its length. the distance from the wire line. So current by distance. So amperes per meter. That is AL minus 1 is the dimension for that. In optics, luminance is candela for area. So how much area the light is passing through. That is given by CD m minus 2. Any matter concentration is given by moles, number of moles present in the given volume, that is moles per meter cube, that is MOL L to the power of minus 3 is the dimension for that. Like this, many more dimensions depending on the physical quantity we are talking about can be retained. And then coming to these are all derived units. Now supplementary units, there are two supplementary units as far as the, the units are concerned, and they are mainly useful for describing the circular motion of the body in a circular path. So, when a body is moving in circular in a plane or in a space, these degrees, these angles, the displacement of the body is explained in terms of angular displacements. So that is in a given time how much angular motion the body is having in the circular path. So in two-dimensional motion, there is planar motion. This angle is called radian, and in case of three-dimensional motion, spatial, it is steradian, which you can see in these two pictures clearly. In the plane angle, that is when the body is moving in a circular or radius r with this origin at O, at a time when the object is at P and when the object is at Q, it subtends an angle theta by the arc PQ. If the arc length is S, S by R gives the angular displacement theta. So this theta is angular displacement. So theta is given by S by R. If S is equal to R, then theta is equal to 1. So when the arc length and the radius of the circular path are same, that then the angle made by the particular arc at the center is known as 1 radian. Similarly, solid angle or steradian. Solid angle is suppose in a sphere. The sphere, when you cut section, you can see a circular section. That is what is shown here. Is a part of the sphere, section of the cut sphere. So this, if the area of cross section is A, this area of cross section is subtending an angle omega at its center, and if R is the radius of the sphere, then the angle subtended omega is given by area by R square, radius square. Area is the cross section area of the conical section. If the area is happen to be 1 meter square and radius is supposed to be 1 meter, then the solid angle will be 1 steradian. These two are supplementary angles. And similarly, we can have large numbers, and because physics deals with very small numbers to large numbers, whether it is a length or mass or time, it covers wide range of the quantities. Few examples are here. For large distances, astronomical unit AU is 1.496 in 10 to the power 11 meters or 10 to the power 8 kilometers. Similarly, light year. The distance traveled by the light in 1 year is called light year. That is equal to 9.46 into 10 to the power 15 meters. That is 10 to the power 12 kilometers. Similarly, parsec. Like we have seen in the circular path radians, if the arc length is 1 angstrom, that is 10 to the power 8 meters, and if it is subtending an angle of 1 degree, then the distance, the radius, the arc length to center radius is called parsec per lactic second. That is the distance which an arc of length 1 angstrom subtends at its center an angle of 1 degree. This parsec is 3.08 into 10 to the power 16 meters. So theta is equal to arc length by radius So these are the such some examples for explaining about large distances. Small distances, similarly, 1 angstrom unit is centimeter. If you millimeters to centimeters, if you divide, then 10 to the power of 8 minus 8 centimeters is 1 angstrom unit. That is 10 to the power of minus 10 meters. Similarly, 1 Fermi is 10 to the power of minus 15 meters. 1 nanometer is 10 to the power of minus 9 meters. 1 micron is 10 to the power of minus 6 meters. And small mass is 1 atomic mass unit 1.66 into 10 to the power of minus 27 kgs, whereas the mass of the Earth and other planets, they are in 10 to the power of 30 kgs, like that. That is large masses. So this is what we learned about the derived and supplementary angles and some idea about units and dimensions and dimensional analysis. Hope you enjoyed the video. Hope it is useful to you. Thank you.